Welcome back. We were discussing about groups in the last video, and although we do not have a lot of time in this course to discuss about groups in detail, but avoiding it causes a lot of trouble. So, what I will do is make discussion enough so that things are a bit easier. Okay, so that's the plan. So, I will continue with the discussion of groups, and if you recall, we have already defined what a group is. Okay, and in that definition there was only one operation that was defined. Okay, that the set has there is a multiplication that is defined on that set. Okay, so you can multiply two elements. Okay, just a second. There was some noise from outside. There still is. Anyhow, so there is only one operation that is defined, which is what we call multiplication. Okay, and in general, if you multiply an element A times element B, okay, it will give you some element C, but multiplying in the reverse order, B times A may not give you C. Okay, in some special cases it can happen, but in general it will not happen. So, when it happens that A times B is B times A for all the elements, that is called an abelian group. Okay, meaning for all elements A and B, this is true. Okay, and in general the groups are not abelian, so they are called non-abelian groups. Okay, recall that I gave a simple example where a group G was containing just two elements 1 and minus 1, and the multiplication was defined to be an ordinary multiplication, right, between real numbers. And this formed a group because all the four properties of a group were satisfied by these two elements. Okay, and we have also seen that Lorentz transformations form a group. We also noted that if you take a subset of Lorentz transformations, which is proper orthochronous transformations, remember that is the one which determinant of a matrix equal to 1 and lambda 0 0 term to be positive. Okay, that those set of elements also formed a group under the same multiplication law, under the same multiplication. And that is, if so happens, you say that that subset forms a subgroup of the bigger group. So, proper orthochronous transformations form a subgroup of okay, of the full set of Lorentz transformations. Okay, and remember, you have to have the identity element. So, this subgroup should have the identity element of the full Lorentz group, right. So, this identity element has to be shared with all the subgroups if there are more than one subgroups in the full group. Okay. So, that is what we discussed. Now, I will do a few more examples so that we understand better about groups. And groups is a very useful mathematical tool or language that we will use or we use in quantum field theory. Okay. So, even though I may not, in fact, I will not be talking about all the groups that are discussed now in this course, but it is nevertheless useful to have them learned in the beginning of the course on quantum field theory. Okay, so when we have another course on quantum field theory, which I plan to have, these things we can directly use. Okay. So let me give you a few examples. So think of the following. Suppose you take all the numbers which are given by this, okay, where theta is a parameter, real parameter, theta is real, so it's a parameter, I is the square root of -1. Okay, so let's call these numbers as u of theta. So I am looking at the set of all numbers which are written as e to the I theta, okay, where theta takes real values. Now I claim that this set forms a group. All these elements form a group. Okay, so let's check about closure. So, and by the way, you should ask what is the multiplication I have defined. Unless I define that, there is no meaning to talking about a group. And multiplication is ordinary multiplication between complex numbers. So that's the multiplication law that I have. Okay, so let's see whether closure is satisfied. So I take an element u of theta 1, multiply with element u of theta 2, then what I get should be again an element within the same set. Okay, so let's check that. It's obvious because this is e to the I theta 1, times e to the I theta 2. This I can write as e to the I theta 1 plus theta 2, and theta 1 plus theta 2 is again a real number, which means e to the I theta 1 plus theta 2 does belong to this set. Okay, so closure is true. Associativity is true because multiplication of complex numbers is associative multiplication, so that is also true. Then identity. Do we have an identity element? Yes, of course. If I put theta equal to 0, then I have 1, okay, and 1 times e to the I theta gives you again e to the I theta. So theta equal to 0 corresponds to the identity element. So there is an identity element. Associativity is true, closure is true. Do I have an inverse for each element? And that's also true that we have. So suppose I am given an element e to the I theta, okay, then e to the I minus theta. This guy, when you multiply with e to the I theta, gives you identity, okay, and that's true for any theta. So we do have an inverse for all the elements. Okay, so this forms a group. This set of numbers form a group, and this has a name. It's called U1. Okay, this group is called U1. 1 meaning you have only one independent parameter, which is theta here. So it's one dimensional basically. Okay, so there is only one parameter theta. That's why you have 1 here. And U means unitary. By that I just mean that if you take a U dagger, multiply with U, you get 1. But here this dagger is superficial because it's just complex conjugation. Okay, so the name U comes from unitary, so you can call it a unitary group of dimension 1. Okay, I have not defined what is the dimension, but unitary group of 1 cross 1 matrices, you can call it like this. Okay, so that's one example which is okay. Now let's move on to something else. Now I want to talk about another group. Let me say this is example number 1. Now let's look at example 2. Now show that which is an exercise. This example 2 is an exercise. Show that all 2 cross 2 unitary matrices form a group, and multiplication I should specify under matrix multiplication. All. Okay. So that is what you should do. So take all 2 cross 2 matrices and show that that set forms a group. So what you have to do is check whether, if you multiply 2 matrices which are unitary and 2 cross 2, whether they give you again a 2 cross 2 matrix which is unitary. That should be easy to check. Then second is associativity, that is automatically satisfied because matrix multiplication is associative, so that is done. Third is identity, and of course you know identity matrix 2 cross 2 will serve as an identity in this set. And fourth is inverse. So you should be able to convince yourself that for each 2 cross 2 unitary matrix there exists an inverse. Okay, and if this is true, then this set will form a group. Okay, another exercise, which is an example and also an exercise. So by the way, this one is called U2. Okay, set of all 2 cross 2 unitary matrices. So it's a group of 2 cross 2 unitary matrices. Okay. Now show that if you take a subset of this, and which is the following. So you take all the 2 cross 2 matrices, 2 cross 2 unitary matrices whose determinant is 1. Okay. Then this also forms a group under matrix multiplication. So it means it forms a subgroup of U2. Okay, and that is what you should be able to do. Not difficult. So here the only additional thing is you have to check that if you multiply 2 matrices which have determinant 1, what you get is again a unitary matrix with determinant 1. Okay, so that should be easy, and if I remember, that was that also happened in the case of Lorentz transformations when you were looking at the proper orthochronous part of it. Okay, so it's the same kind of same exercise here. Now let's look at SU, a more generalized version of this. In fact, there is not much to prove. If you have done the exercise 2 and 3, this one is automatic. Show that all n cross n unitary matrices form a group. Okay, same reasoning will give you, and this is called UN. U stands for unitary and n for n cross n matrices. Okay, and obviously you can expect that if I look at a subset of this where the determinant is 1 for all the matrices, it will also form a group. So show so all the elements in the group which have determinant u equal to 1 will also form a group, and that's a subgroup, and this one is called SUN. So U is for unitary, N is for n cross n, and S means special. Okay, and why it's special? It's special because determinant U is 1 for those elements. Okay, so it's called special unitary matrices. Okay, so please show that this SUN is a subgroup of UN. that you should be able to show. Now, I will talk a little more about SUN. See, right now we are doing pure mathematics. Physics will come after some time, but this is important. So, let us look at SUN. They are unitary matrices, which means U dagger U is equal to U dagger, and that is equal to 1. Okay. But on the top of it we said special unitary, which means determinant of U is also equal to 1. Okay. Right now when I am writing U is an arbitrary element of these groups, okay, of SUN. Okay. So, I am denoting the elements of the group by this capital U. Okay. So, now what I want to do is I want to see how to generate all the possible elements of this group. Okay, that is what I want to do. I want to understand how to get all the elements of this subgroup or group. So, let us see. What we will do is the following. So, if you have n cross n matrix, how many entries you have? You have so if you count all of these, this is n cross n, so it will be n square entries. Now, each n square entry is complex. Okay, so when I am looking at an arbitrary complex n cross n matrix, see I am starting with the most general thing. What is the most general n cross n matrix which I can write, which is complex? It is this. It will have n square complex entries. Okay. So, the most general, right now this is not unitary, I have not imposed any constraint, I am just writing n cross n complex matrices. So, you have in total n square complex entries, but each complex entry is a sum of 2 real entries, right. So, if this one, let us say I call Z1, then Z1 is x1 plus I y1. So, x1 and y1, they are in your hands, right, that you choose. So, these are two real numbers. So, when you are looking at n cross n complex matrix, you have freedom to choose 2 n square real numbers or parameters. Okay. So, there are parameter, there are 2 n square real parameters that parameterize this matrix. Okay, that is good. Now, I want to know about SUN. So, what I will do is I will count how many constraints there are. Okay. So, given total number of parameters that I have minus the total number of constraints, that will give me what are the total number of independent parameters that will parameterize a SUN matrix. That is what I am doing. So, let us see constraints. So, first constraint is easy, determinant U is equal to 1. So, as I said, we have to count the constraints that we have. So, we are going to look at U dagger U equal to 1, what constraint it gives and what constraints you get from determinant U equal to 1. So, determinant U equal to 1, let us do that one first. So, U dagger U equal to 1 implies that if you take the determinant of the matrix U, it will be a phase, it will be e to the I alpha. Okay. Because when you are taking a determinant of this, it will become determinant of U times determinant of U dagger. Okay, and on the right hand side it is a unit identity matrix, so determinant of identity will be 1, and this gives you determinant of U modulus square is equal to 1, which means determinant of U is a phase, okay, e to the alpha. So, that is true in general for unitary matrices, but now we have on the top of it put a constraint that determinant of U should be 1, which means that this parameter phase is not arbitrary anymore and you have to restrict it. Okay, and let's take it to be alpha equal to 0. You are allowed, you cannot continuously change it. This parameter alpha you cannot continuously change, it has to be fixed. So, let us take it to be alpha equal to 0. So, that is one constraint. Okay. Out of all the different parameters that parameterize this matrix U, one freedom is lost. Okay. So, there is one constraint. Now, let us see what else we get from this piece. Let me also remove the timeline. So, let us see. Now, I am going to find the constraints in two parts. One, I will look at what happens on the diagonal, okay, and then I will look at what happens on to the remaining entries. So, let us look at the diagonal entries. So, I take U dagger and take say an arbitrary element will be alpha beta, or let us call it alpha and beta. But now I am not looking at alpha and beta, I am looking at alpha alpha, and this is your delta alpha alpha, okay, whatever that number is, and that number it is 1 because it is unity. Okay, so I am looking at only the diagonal entries. Now, U dagger you can write as U alpha beta U dagger beta alpha. Okay, there is no summation over alpha. I am not implying any summation. Okay, this is same as U alpha beta. Now, U dagger is a star and a transpose. So, if I put a star here and then I am only left with transpose, and I do transpose by interchanging these two indices, it becomes alpha beta. Okay, let me make it explicit. Here there is a summation over beta, but not over alpha. Okay, it is matrix multiplication. So, I have this. Okay. Now, U alpha beta times U star alpha beta is just, and this is a real number, it is a modulus square of a complex entry. So, we are U alpha beta are these entries, right, this entry. So, this entry is U 1 2. So, here we are saying that it is a sum of all these that has to be 1, okay, but each of this is a real number because it is modulus square of a complex number. Okay. So, how many equations are these? How many constraint equations are these? I should not remove. Okay. So, how many are these? You have n values of alpha. So, alpha takes value 1, 2, 3 and so forth. Beta is anyway summed over. So, these are n real equations. Okay. So, you have n constraints. So, this is important because unless I know that these equations are made up of real numbers, I cannot say that these are n equations. Then I will have to say 2n equations because equation could be complex, right. So, this is what I have showed, that there are n real equations as constraint coming from here. Now, let us look at off diagonal entries. Do I need more space? Okay, maybe here itself. So, if I look at off diagonal entries, so let us go back to this equation. You have U dagger alpha beta is 0 because delta alpha beta is 0, and I am saying alpha is not equal to beta. Maybe I should go to the next one. U dagger alpha beta element of this is delta alpha beta, and I am saying alpha is not equal to beta, that is 0. Okay. Now, this I write as U alpha gamma U dagger gamma beta is equal to 0. Okay. And so, that is one equation, that is an equation, and there is a summation over gamma. So, how many alpha and beta I have? How many equations are these? See, total there are alpha and beta take values from n to n. So, we have already removed these entries, right. So, these out of n square, these are gone. So, these are n of those. Okay. But then you realize that, see, let's say alpha is 1 and beta is 2, and I have such an equation. So, you have u1 gamma, u dagger gamma 2 is equal to 0. Okay, let me write it down. u1 gamma, u dagger gamma 2 is equal to 0, then there is a sum over gamma. Now, these are complex numbers, right, these ones. So, this is a complex equation. Okay. So, these are two real equations, one for the real part, one for the imaginary part. So, these are two real equations. But then we realized something else. Let us look at not so here right now, here in this one I have taken alpha as 1, beta as 2. Let us take other way around. You take beta alpha, this one, where alpha is 2 and beta is 1. Let us see what happens. Then you get u beta gamma, u dagger gamma alpha equal to 0. Okay. Now, what I will do is I will take this equation and takes a complex conjugate of it. If I take a complex conjugate, then I get u beta gamma star u okay, let me, before I do a complex conjugation, let me write it slightly differently. And also this one I want to write as first u alpha gamma u star beta gamma. Okay, because of the transpose I have taken care of already, I have interchanged the indices, and that is what I want to do here. So, I first write it as u beta gamma and u star alpha gamma. So, I have taken care of conjugation, transpose. Now, I do a complex conjugate of this. See, if x plus iy is a constraint, then x minus iy is also, right. It does not change anything. If this one is saying x is 0, y is 0, this one is the same thing, and these are related by complex conjugation. So, I take complex conjugate of this and I get u beta gamma star u alpha gamma equal to 0. And you see this one is exactly the same as this one, u star beta gamma u alpha gamma. So, what has happened is, when I, instead of looking at 1 2 element here, I looked at 2 1 element. Okay, they have become equal, they are same. Okay, they are related by actually complex conjugation, not equal, but they are related by complex conjugation. So, that is not giving a new constraint to you, it is the same constraint which is appearing from this one also. So, which means that all the constraints that you are going to get from here is the same constraint you are going to get from this part. So, this part does not give you a new constraint, it just tells you, repeats the same constraint. So, our independent constraints come from this one and this part. Okay, and these are that is fine, but also another point that these constraints are not real, these are complex. Okay. So, how many are these? See, total was n square, out of which if I remove the diagonal, I have minus n. Okay. I am looking at only the upper half because lower half is fixed by that. So, I should be looking at only this part. This is all the elements in here, but these are complex equations. So, each of them is two real equations. So, I should multiply by 2, and that is n square minus n. Okay. So, how many constraints do I have? I have these ones, n square minus n, total constraints. I have n square minus n, but then I had one more coming from the determinant part. So, these are the total number of constraints. So, n square minus n minus 1, let me write. total number of constraints n square minus n, sorry, plus 1, I should not write minus 1, this is one additional constraint, okay, plus 1. Now, let us see how many independent parameters we have to parameterize a unitary matrix. So, independent parameters that parameterize the unitary matrix is, to begin with, we had n square complex parameters or 2n square real parameters. Now, I have these many constraints which I should remove, and that gives you n 2n square minus n square is n square. So, something has gone wrong, let us see. Nothing went wrong, I just missed a piece. So, let me do this. Total constraints here, these are from the upper half, okay. That is fine. This is not total constraint, this is n square minus n. This is from the upper half part which I calculated here, okay. So, now let us do it again. So, total number of constraint is n square minus n, this is coming from upper half, plus you had n real constraints coming from the diagonal entries. Let us go back, right, this one, these were n constraints coming from the diagonal. So, that is correct. Then you have one more constraint, because you have coming from determinant u equal to 1 from the phase part, okay, that is what is here. So, this is the one which I had missed, okay. So, now I should write 2n square minus, these two cancel. So, this is n square plus 1, because this is gone, and this is n square plus 1. So, this should be removed. So, you have 2n square minus n square is n square minus 1, correct, finally. Oh, good. So, hope everything is fine. 2n square minus n square is n square minus 1, that is correct. Okay, after this scare, we have the right answer, okay, which means that if I am looking at SU2 group, how many independent parameters I have? It is 2 square, which is 4 minus 1, which is 3. So, 3 independent parameters. Okay, so, 3 independent parameters parameterize the elements of SU2 group. How about SU3? So, let us see, 3 square minus 1, 3 square is 9 minus 1, 8. So, this is equal to 8 independent parameters. Okay, that is good. Now, I want to talk about a little more about these groups. So, let us go back and go here. So, I am now going to look at so let us say I am looking at a unitary unitary group, SUN group, and I have already shown that it is parameterized by alpha n square minus 1 parameters. So, okay, these are all the parameters that you have for SUN. Okay. And I parameterize in such a way that if all the parameters are equal to 0, you are sitting at the identity matrix. Okay. If all the parameters are 0, right now not 0, so I am going to write more terms, but you know you are at the identity element when all the parameters are 0. That is what I am choosing as the way of parameterizing. Okay. Now, if you are slightly away from identity, infinitesimally away, meaning you choose the parameters alpha to be infinitesimals, then you will be slightly away from there, and let us say that infinitesimal deviation you have from identity is given by h, and this is I am saying of order alpha. Okay. So, generically this. So, this is linear in alpha plus all the higher order terms, which I will generically denote by order alpha square. Okay. Now, let me look at what u dagger would be of this. If I take a dagger, I get minus I h dagger. Okay, I am dropping the. Okay, let us keep it for a while. Now you know that you have the condition that these are unitary. Okay, this implies that if you take the product, you will get 1 plus I h. Now I am dropping the order epsilon square terms. No, sorry, order alpha square terms, and right now alpha are infinitesimal. Okay, so alpha is infinitesimal. So I have 1 minus I h dagger, and this should be 1 identity. These are all identities. This gives you identity minus plus I h minus I h dagger plus a term which is h h dagger, but that is of order alpha square, which I am dropping. Okay, so I leave those pieces. This is 1, and this tells you that h is equal to h dagger, meaning h is Hermitian. So, the h has to be Hermitian. Okay. Now, I will write u as the following. So, u alpha 1 to alpha n square minus 1 is 1 plus I. Now, H is a Hermitian matrix, n cross n Hermitian matrix. What I will do is I will write it as n square minus 1 independent Hermitian matrices. So, I will write it as a linear sum of Hermitian matrices. So, now this H are constants because I have pulled out the parameter alpha. So, this is the linear sum which will constitute the H for you. Okay, so, summation over I am sorry, there is another I here, but this I is different from this. So, this is running from 1 to n square minus 1, okay, plus all higher order terms in alpha that's there. Okay. Now, exercise which is fairly easy, check that determinant u equal to 1 imposes a constraint on H. You see, u is 1 plus these numbers, which you can put whatever you wish to, okay, times H. So, H is the object which should know that u is unitary, and it knows that by this property that H has to be Hermitian. So, but then it should know more, it should know that determinant u is 1. So, there should be something else which H has to satisfy, and that is the fact that H is traceless. Okay, so, check that determinant u equal to 1 implies that H is traceless. Please do this exercise, and these H are called the generators. So, these H i's are called the generators of SUN. Okay, these traceless Hermitian matrices are called generators of SUN. So, for SU2 you have 3 generators, for SU3 you have 8 generators. So, SU2 you have 2 generators which are traceless Hermitian matrices, and for SU3 you have 3 generators which are traceless Hermitian matrices. Okay, SU2 and SU3 are important groups because your entire understanding of fundamental interactions, okay, that of that is electroweak interactions and strong interactions. They are based on SU2, U1 and SU3. Okay, so that's why I am discussing here. I mean, not because I am going to cover those interactions here, but it's useful to know these things. Okay, and that makes also understanding Lorentz algebra, Lorentz group easier, or rather it's needed to understand that group. Okay, so now I have said that there are three Hermitian traceless matrices for SU2. Okay, I want to construct those generators for SU2. So I want to pursue SU2 further and construct the generators. And you are going to see something nice if you have not already seen that before. So let's write arbitrary Hermitian matrix as this. So let's call it Z1, Z2, Z3, Z4. Okay, that's an arbitrary matrix, complex matrix, 2 cross 2 matrix. But then I say that H dagger should be same as H. So H dagger is H1 star, sorry, Z1 star, Z2 star, Z3 star, Z4 star. That's the dagger of it, Hermitian conjugate of it. And the fact that H dagger is equal to H gives you the following, that your H is this. So Z1, this should be equal to Z1 star, which means, just a second, I should remove it. So Z1 is equal to Z1 star, which means this entry is real, and I want to call it a real number. I will call it gamma. Okay, so gamma is real. Then I have Z4 star, which has to be same as Z4. So that is also going to be real, and I call it something. Let's call it beta. So beta is located here, okay, at this place. Okay, but then I remember that my matrix has to be traceless. So gamma plus beta should be 0, which means beta is minus gamma. So I'll put a minus gamma here. Okay, and then you have a Z3 star. Oh, sorry, Z2 here. So I write Z2, and here instead of Z3 I should write Z2 star. So Z2 here and Z2 star here, so they are complex conjugates of each other. So for Z2 I write alpha minus I beta, alpha minus I beta, and here it's complex conjugate, so I write alpha plus I beta. Okay, if you had put a plus sign here and minus sign there, nothing changes. Okay, it's just the parameters, you can change the sign later. So there is nothing big going on here in choosing the signs. So that's my Hermitian matrix. I have taken care of H, it being Hermitian and also tracelessness. So I can write it as the following: gamma. Okay, maybe let me write it slightly better. So I take the alpha part, so alpha, and I put everything else to be 0. So I put all the parameters to be 0 and I have only alpha, so I get 0, 1, 1, 0. Then I have beta, so I keep only beta non-zero and everything else 0. Then I get 0, minus I, 0, plus gamma, that's only on the diagonal, and that's 1 minus 1, 0, 0. Okay, does that appear familiar to you, these matrices? See, these are the Pauli matrices. So this one is sigma 1, this one is sigma 2, this one is sigma 3. So note that sigma 3 is the one which is diagonal. Okay, and you already know that they do not commute. So, you can multiply these two and in different orders and check the difference, that will not be 0. So, matrices do not commute in general. So, let me write. So, where sigma 1, sigma 2 and sigma 3, these are Pauli matrices. So, you see why you have gotten these matrices. These are basically the, apart from some factors, these are the generators of Pauli matrices, sorry, the generators of SU2. Okay, good. Now, check that if you take sigma I over 2, I am dividing by half, you will see immediately why, sigma j over 2, and look at this commutator, you get I epsilon I j k sigma k. This I believe you have seen in your quantum mechanics course. Okay. If I do not put a 2 here, it will start showing up here on the right hand side. So, that is why there is a factor of half. So, this is the commutation relation which these matrices obey, and you have already seen this in a previous class. Let us see, I think somewhere here the same commutation relations you have seen. You see the commutation relations of Ji and Jj, they are exactly the same, right. It is again you have I epsilon I j k. Okay. And so, you can understand that these commutation relations are of SU2 are important even for Lorentz group. Okay. So, now any element of SU2 can be parameterized using Pauli matrices. I will jump a bit. Okay, I will again come back to that later, but I will just say here without telling you why I am saying this, that any matrix of SU2 can be written as e to the I, some parameter, let us call alpha I, sigma, I can put I up there is no, or maybe a k, sigma k over 2. So, there is a summation over k. Okay. So, you have sigma 1, alpha 1, sigma 1 over 2 plus alpha 2, sigma over 2 plus alpha 3, sigma over 3. Okay. And these are the generators. These are the generators of SU2. See, H was generator. Here you can always multiply a half here, right. You can overall and absorb the 2 in alpha, beta and gamma. So, you take these as the generators, because then commutation relations are nice like this. Otherwise, there will be a factor of 2 coming. Also check the following. Check that if you take the trace of let me call the generators to be Ta, and which is sigma A over 2. Okay. So, this Pauli matrices divided by half, they are called the generators, and usually they are denoted by Tas. Okay. Generators of SUN groups are denoted by Ta, that is a standard nomenclature. So, show that if you take Ta Tb and if you take a trace of it, okay, then what you get is delta AB is proportional to delta AB. In fact, it is half delta AB. Okay. Check this property that this is indeed true. Okay, I think